Hello, everyone. My name is Reshef, and I'm the VP Products for Varada. In this talk, I would like to discuss how adaptive indexing and dynamic materialization wrapped with Presto is the next step in interactive analytics on top of data lakes. For the last 15 years, I've been building and implementing analytics solutions in the domain of customer and brand relationship. These systems that we worked very hard to build and to implement provided business-critical information either in real time or post-mortem, so that business executive, business analysts, product marketing, etc., basically human beings, can take knowledge-based business decisions. These systems were based on various streams of data. It was either phone calls or chats or reviews or click streams. It was IoT-based, so very rich data and very interesting ones, so the decisions can be made based on that. The success of these systems was always due to a balance, but one criteria, but a balance of three things. Did we deliver the right information at the right time with the right cost? It's a very delicate balance between the business needs for information and for knowledge and the cost and the TCO of it all, to bring it all to the business. How do we bring human accepted performance at the right cost? This is a constant challenge in every organization I've worked with around the world. Of course, the petabyte scale data lake changed everything. We will talk about it in a couple of slides. This balance was solved for many years using the traditional data warehousing approach, meaning that data was either pre-aggregated or very strictly modeled and reduced to a size of, we're talking rows, a couple of hundreds of millions of rows, not beyond, so that human or SQL consumers can get the answers in less than 10 seconds. That's kind of the golden rule for interactive analytics and for business decision making. The interactive analytics for each query, the time of response for each query needs to be under 10 seconds. And that was solved again in the data warehousing by modeling and by aggregations. It all changed with the huge revolution. I think everybody was excited at the time and until today by the revolutionary white paper of Google published in 2004. It really changed the world and enabled big data and big data analytics, introduced Hadoop, MapReduce, and the usages of that, and started building data lake-centric architecture to enable business analytics. This revolution increased the business potential and the business hunger for information, longer trends. If we talked about the constraints before, now the trend analysis can go over, not over 1 month, but over a year, 2 years, or 5 years, and then you can gain much more insights. But this was a very hard task from the engineering side. Why? Because of two main reasons. One, you needed to code MapReduce algorithm in Java, so it reduced the population that actually could use efficiently and query the data. So that you had the bottleneck of needs and questions, but very little people to actually do it. It used very large files of storage. The recommendation was 128 mega columnar-based data objects to make in one read many operations, so the MapReduce would be efficient. But that created slow time to market. The queries ran actually very slow. If anybody here used MapReduce Java on Hive, and waited a long time for a query to come back, you understand perfectly the problem. The next leap was done by the guys at Facebook, three guys that we all know and love. Martin, David, and Dane wrote Presto. And Presto was the next step in big data analytics to try and solve these problems of speed, of cost, and of ease of access to the information. So the first revolution for me that Presto did was changing from Java-based coding to SQL. SQL is the language of database. SQL made it actually democratized the ability to query big data. So that's the first thing that Presto did. At the same time, Presto also hid the complexity of MapReduce by doing it under the hood and giving, again, a perfectly simple SQL query engine. That was an amazing revolution. It enabled, and you see the usage of Presto around the world. It's just mind-blowing, and how quickly Presto evolved, showing that this next step was necessary in big data analytics. But still, we're looking at large files, and performance is an issue. If you want to gain performance, you need to put cost, like in a lot of cases in technology, you need to put more machines. And this balance, again, remember the balance of the 3 points, the business needs, the performance, and the cost, was still very delicate to do, but manageable, way more manageable than doing it with Hadoop and Java query. Varada took a new approach and tried to solve the performance issue by kind of putting everything, the first paradigm of large Parquet file completely upside down. Now, Varada tried to build a new physical bed using storage and networking technology for the data. Instead of large chunks, very small chunks of data. And the technology that we used was SSD storage for random access and NVMe over Fabric for the networking and latency. What was the idea of this new physical bed for big data? NVMe enables separate servers in the cluster to see, so the CPU of server A can see the storage, the SSD storage of server D, as if it was physically attached with very low latencies. This is one capability that was leveraged. The second, we wrote in C and we reprogrammed the virtual SSD layer into very small, what we call nanoblock of 1 kilobyte of size. So 120 mega from the Parquet transformed into 1 kilobyte of storage unit. That's the first idea. Then we said that in order to run fast, we need to index. So how can we now, with this physical bed, add indexing and make it run very fast? Now imagine this network of hundreds of millions of small nano blocks of SSD. And now we're going to look at the data, or at the actual table, in two ways. One in a columnar perspective, and the other one is in a nanoblock perspective. Actually, in a third way, in the index perspective. Let's combine these three. So we go down to the data lake and go to these huge tables, go to one column of this table, and look at the size of one nanoblock. 1 kilobyte is equivalent to approximately to 60,000 rows in one column. And now we're going to read the actual values and the data in one column. So instead of indexing the entire column and using very large and complex indexes, we're going to index very small parts of the data. So if I have, like in this example, a temperature column in an IoT scenario, and temperature will go, I apologize in advance, I will talk in Celsius, and we'll go from 0 to 100. So I have 101 values to index, but instead in this chunk of 60,000 rows, it was a time where temperature was between 31 and 32, two values. I will optimize an index to index only two values, not 101. glue it to the data, and push it to one nanoblock. And this is the way that I'm going to ingest the entire table. The end result of it would be this network of hundreds of millions of nanoblocks, all in random access, all holding optimized adaptive index to the type and cardinality of the data. And this will enable me to run very, very, very fast on indexes and pinpoint the data that I need, take it out, and push it up to Presto for presentations. Where this technology helps the most, you can imagine that where indexes are leverages in filtering. Here you see a case where the index will accelerate this query by up to 300 times faster than most of the solutions. We run from X100 to X300 in this kind of scenario. You see different kinds of filtering, and in a couple of slides we'll talk about the scan and filter operator and how you can detect it and see if you can accelerate using indexing. Here you have the condition. The more conditions you have, the nearer the selection is, the faster you go on the index, and you pinpoint the exact data chunk that you need. We use adaptive indexing, as I explained, to random access and very quickly, in an independent way, access each block. But we also have several types of indexes. In this case, you see a string, integer, and also regex on text using the Lucene indexes. So adaptive, variety, small indexes, random access. This is how we solve the indexing of big data. And that was dreamy. We got tremendous performance, and you can see benchmark where we're extremely, extremely fast. But coming to the market, we saw that that's not the end of it. There is still this triangle to solve. There is still the cost, performance, and business needs, where TCO is a big actor in this equation. So what did we found out in the last couple of years? So indexing is great, it works great, it accelerates, but still there is a price to pay, and it needs to be extremely precise and solves a specific set of business problems. The other thing, and the way that we at Varada solved it, is we used a fully indexed, synchronized, materialized view, which meant for the users to hit Varada and not their Hive and their Hive table. So indexing is great, but it needed an upgrade to be able to run in production and to be, again, able to balance this delicate trio of requirements. So we did a lot of investigations, and we studied millions of queries and workloads to understand how we can improve that in a smart way. We had an aha moment where we had a customer who had this huge table. This is an IoT use case, where you can see the numbers. Huge table, really huge table. So it was not billions, in 1.6 trillion, I think, rows in this table, and the width is 1.3K columns. Crazy table, which we managed to put to index, and again, queries ran actually very fast. But imagine the size. The cluster would be pretty big, and we needed to do something about it in a smart way, because our customer really liked the speed but didn't like the price. Again, the balance needs to be solved. We studied the workload, how this table is being queried, and we scanned 15,000 queries in this case. And we discovered that from this large number, only a much smaller number, and you can see the graph and the long tail of how this table is being hit and which columns are being hit. And we said, okay, this is an aha moment. We do not need the entire table. We need to be very smart. We need to materialize what is really needed to materialize in a dynamic way, because it will change, and we need to understand very quickly what is being queried, what is the business requirement, and automatically adapt the infrastructure to the business needs. Still keeping the indexing, still keeping the speed, because this is the right time factor. So we took both worlds and took the dynamic materialization, decide which column needs to be materialized. In what way this column needs to be materialized? Do we need, and again, this all needs to be learned in a continuous way from the queries. So which columns are being queried? How are they being queried? So we'll know which type of materialization we need to do to each column. Is this data-only materialization, index-only materialization, data in index to increase performance, or nothing? This, as I mentioned, this Varada technology is wrapped around Presto and going directly to the Hive tables to save cost. But we need to understand the question to understand how the materialization should be performed and apply indexing where and if needed, and again in an adaptive way. This took us to the next level. We took out a tool that will be soon available as open source. We'll open source this. It's already, you can go to our website and check it out. So if you're a Presto user, you can actually test for yourself how your cluster is performing and what type of questions and what type of who are the users, who are the tables, and who are the columns that are being queried in your context. This is basically made out of three Python scripts: one that will collect the queries, the other one that will summarize and analyze, and the third one will analyze and produce this kind of reports to you, showing you all these graphs, who are the users, the selectivity that will give you good hints on where indexing might help you and where it can help you, where do you spend your time, and which operator is being executed the most in the queries. That will also give you a good idea of what is the nature of your queries and how selective and how filtered, how much filtering are you using. In this case of anonymized data set, scan and filter operator is used in 80% of the cases, so indexing would be a perfect fit. So again, the combination of dynamic materialization, which column, what type of materialization, and what type of indexing is a big leap forward in what we see towards balancing between those three criteria: the business need, the TCO, and the performance. A quick case study that we had from one of our customers, which is in the cyber security space. Again, the classical big data environment. Lots of events streaming in from tens of thousands of devices. Needs quick analysis, and from the other side, the business demand kept growing. Their major customers asked them for more and more post-mortem analysis on more days. So if their current solution gave sufficient solution, a good solution for 7 days analysis, their customers went to 30 days analysis and 90 days analysis, still keeping the performance criteria of under, in their case, 8 seconds. They were more exigent than the others. Studying what to materialize using the adaptive indexing, we've built a solution that you can see was 100 times faster, lower in TCO, and increased the historical analytics from 7 days to 30 and 90 days in production. I would like to thank you very much for listening, and I'm here for any questions you might have. Thank you very much.